Welcome back to the Mechanics of Solids lecture series. In this video we're continuing with the example we started in the last video, which was an example of a parallel bars bonded together subjected to an axial force P of 25 kips and a temperature change delta T of 58 degrees Fahrenheit. We're finding the stresses and the deflection at the end of each bar. From equilibrium, we found that the internal force in member material 2, F2 equals 25 kips minus F1, both assumed to be in tension, and our compatibility equation that the deflections were equal, and it reduced to this equation right here. So I'm going to start with the compatibility equation. Sometimes it's preferable to substitute known values in. In this particular case, I'm going to manipulate the equation until I can isolate F1 and then substitute all the values in at the very end. And this is sort of a matter of preference. You can try different approaches. For this particular problem, I think it's a little bit easier to substitute at the end. So let's go ahead and manipulate a little bit. F1 over A1 E1, I'm going to bring both forces to the left-hand side, minus F2 over A2 E2. I'm going to bring the thermal coefficients to the right-hand side, and I have alpha 2 minus alpha 1 times delta T. Okay, and I am now going to substitute in my equilibrium equation for F2. So I had F1 over A1 E1 minus F2, which is 25 kips, minus F1 over A2 E2 equals alpha 2 minus alpha 1 delta T. I'm going to group all like terms that multiply F1. So I have F1 over times 1 over A1 E1 plus this term right here. The two negatives cancel, and I have 1 over A2 E2. Then I'm going to bring the 25 kips over A2 E2 to the right-hand side, plus alpha 2 minus alpha 1, delta T comes along for the ride. And now I can solve or write an expression for F1, which is 25 kips over A2 E2 plus alpha 2 minus alpha 1 delta T divided by the whole thing, 1 over A1 E1 plus 1 over A2 E2. Sorry, I'm probably getting too low there. Now I'm ready to substitute in some of my numbers, so I'm going to continue calculations over here. F1 equals, let's pay very close attention to units here. We have 25 kips divided by A2, 17.5 inches squared, times E2, 10,000 KSI, plus the alpha 2 minus alpha 1, 13 minus 6.5 times 10 to the negative 6th per degree Fahrenheit times 58 degrees Fahrenheit. So let's look at units. On this side I have kips per square inch, kips per square inch on the bottom, those cancel. And on this side I have per degree Fahrenheit times degree Fahrenheit, so those cancel. So the numbers in the top here, part of the equation, are unitless. This is all divided by 1 over A1 E1, 10 inches squared, times 29,000 KSI, plus 1 over 17.5 inches squared, times 10,000 KSI. Okay? Now what happens to the units on the bottom? We have inches squared times KSI, so the inches squared and the SI cancel out on both of these. And we're left over 1 over kips, which is going to give us kips on top. So that's the units we're looking for, units of force. We always need to do that check. Okay? This is just a lot of numbers to plug into your calculator. You need to do this very carefully. Punch it into MathCAD, any other Excel, any other program that you're used to make it easier. But after doing that, we get something, hopefully 56.7 kips, indicates that bar 1 is in tension. F2 equals 25 minus F1, 56.7 kips, and that's going to give me a negative 31.7 kips, which indicates that bar 2 is in compression. Okay, does that make sense? Certainly, due to the applied load, both bars would be in tension. However, when we consider the thermal loading, we note that bar 2 has a larger coefficient of thermal expansion. So bar 2 is trying to expand faster than bar 1. What's going to happen in that case is that bar 1 is going to pull on bar 2, causing bar 2 to be in compression. It's going to pull back on bar 2. Well, bar 2 pulls forward on bar 1, causing it to be in tension. So those balance each other out there, and that's why we see tension in one and compression in the other. Solve for the stresses. Sigma 1 equals F1 over A1 equals 56.7 kips over the area 10 inches squared, which is 5.7 KSI, which is the units we like to work with for stresses. Sigma 2 is equal to F2 over A2, negative 31.7 kips over 17.5 inches squared, or negative 1.8 KSI. Okay, and finally we want to find that deflection, and coming back to our compatibility equation, the deflection in both bars should be the same. So delta 1 equals delta 2. We could use either expression to find it. Let's go ahead and do, for bar 1, F1 L over A1 E1 plus alpha delta T times alpha 1 delta T times L. And punching in our numbers here, F1 over A1 is the stress. Little shortcut, 5.7 KSI times L1, 85 inches, divided by E1, 29,000 KSI. Those two cancel out. Plus alpha 1, 6.5 times 10 to the negative 6 per degree Fahrenheit, 58 degrees Fahrenheit times 85 inches. The Fahrenheits cancel out, and we are left with 0.049 inches. So that is the deflection. It's a small number, units of inches, and for our sanity check, we expect deflections to be small. We talked about the stresses already. So the numbers more or less make sense, and that concludes this.